All right, so who knows what we were talking about last time, but I think we're going to start here at chapter 6. I think last time before the exam, we finished up chapter 8, if I'm not mistaken. And so we're off to chapter 6 here, followed by chapter 7. They kind of go together. So chapter 6, we're going to talk about equations and balancing equations. And then into chapter 7, we're going to talk about types of reactions. All right, so let's get started here. Yeah. All right. So here in chapter 6, we're going to talk about actually balancing chemical equations and reactions and how to go about that. So first off, how do we know sort of a chemical reaction occurred? There are some signs that allows us to sort of figure that out. A lot of times, some type of chemical or color change is something that really sort of indicates that something has occurred. A solid being formed or a precipitate being formed is definitely a sign that a reaction took place. When you see bubbles, that is usually some indication that a gas is being formed. So when we sort of visually see bubbles occurring in a reaction, that's usually that indication of some type of gas. Remember that really a chemical reaction really happens when we have a chemical change. And when we have a chemical change, what that means is obviously what we start with and what we end up with are two fundamentally different things. And you can't get back your original sort of substance through any type of physical means. Although sometimes it may not be as visual. Obviously, a flame would be visual. So if you did something, you saw a flame. Like lighting a Bunsen burner is an example, obviously, of a chemical change and a chemical reaction is taking place. The methane, the oxygen in the air, a little spark, and you get the flame, obviously. But things like heat as well, or maybe not visual sort of signs that you maybe will see. But if you're holding on to a test tube that gets extremely hot, that means that energy is being released as a result of that reaction. That means it's also an exothermic reaction in that process. Same thing if you're kind of holding on to a test tube, it gets really, really cold. That would mean it's an endothermic reaction, basically absorbing heat, and is absorbing heat from your hand, basically, which is why your hand gets really, really cold while you're holding on to those test tubes. So again, here's an example of a little electrolysis there of water, which you'll do a little bit later today. Not exactly like that. We just don't dump it into the water, but basically all those bubbles that we're seeing is the hydrogen gas and oxygen gases being formed. There's really sort of three or a number of clues as to, again, why a reaction takes place. And again, color change, solid being formed, bubbles, and heat are really big indications that some type of chemical reaction has definitely taken place. Here's some examples here. We'll do something similar to this here, but it's like a precipitation reaction here, pouring two liquids together, and we get this sort of yellow solid that's formed, sometimes referred to as a precipitate, a PPT. And obviously here's our bubbles and stuff and our flame. Okay. So the major way that we represent chemical reactions is through a chemical equation. And the chemical equation basically uses obviously the symbols and the formulas for whatever is being reacted. There's sort of left-hand side, right-hand side of the arrow. And as we'll talk about what each of those things mean. But when we take hydrogen gas and burn it in air, which is oxygen gas, to form water, this is sort of the start of our equation. These are our starting materials over here on the left-hand side of the reaction. And these are what is formed over there on our right-hand side of the reaction in this particular case. When we look at a chemical equation, it's always really important to make sure that it is balanced. And if we take a look at this equation here, we do see a couple of things. First off, it's really not balanced. But if we wanted to sort of read it, a couple of things, we would have molecular hydrogen, which is sometimes how hydrogen gas is referred to, and molecular oxygen, which is also how oxygen is sort of referred to. Remember, in their basic forms, the way they come uncombined is as those diatomic molecules and as gases. So it's a very common mistake a lot of people make. when they come across one of those diatomic molecules we talked about, they just write H for hydrogen or O for oxygen, and they never really obviously be able to balance the equation correctly. So you always want to, in an equation, make sure that you are starting with the correct formulas. And it may not make sense yet, but with the order at which you want to do things is make sure you get the correct formulas like we did with nomenclature and naming, and then you want to balance it. Very often people try to do two things together, like balance it and do the formulas. They usually end up with the wrong formulas, and they never can balance it because they're not starting with the correct formula. So it's really important to keep that in mind as you go through writing equations and balancing equations, that the order is get all the correct formulas down first, regardless of the balancing part, and then go back and balance it. And that's really the sort of correct way to do that. The arrow means to react with or yield, and then obviously we yield what's on the product side. But as I mentioned before, there is a conservation of mass, and we never lose any elements along the way. So when we do look at this equation, it obviously is not balanced. We have 2 hydrogens on the left, we have 2 on the right, we have 2 oxygens on the left, but we have only 1 oxygen at this point on the right hand side. And obviously that is not a correct equation. And that is what is sometimes referred to here as the unbalanced chemical equation. And as I mentioned before, we really don't lose any elements along the way. There's conservation of elements. And that's because in normal chemical reactions, all that's involved really are electrons. And if you remember that the really main important subatomic particle that determines what element you're talking about, it is protons. So since protons aren't touched in any chemical reaction, it's just electrons. Whatever elements we start with, we should end with on the right-hand side of the equation. The difference is they may be in different sort of formulas, compounds on the right-hand side, but if we started with 6 carbons on the left, we should end up with a grand total of 6 on the right, wherever they may be at that point. So this is, again, the unbalanced equation, which is a good first step if you're sort of given everything in words. You want to, again, regardless of the balancing, just make sure you get down all the correct formulas first. Then what we really need to do is balance this equation. So to balance this equation, we actually balance it by only changing coefficients. So when we balance the equation, the only numbers that we could change are the numbers that come in front here. We can never change the subscripts or the numbers in between, because if we change those, then we're obviously changing what it is, and we don't want to do that. So in this case, we would need to sort of balance it. Maybe a couple of 2s would help us here, like a 2 there and a 2 there. That would then give us 4 hydrogens on the left. 2 times 2 on the right there is 4 hydrogens, 2 oxygens there. And again, distributing this 2 to the oxygen as well gives us 2 oxygens on the right. And then we would have our balanced equation at this point. Again, no other numbers should be changed other than those coefficients. Now, this does represent the balanced equation. When we talk about chemical equations, really a couple of important parts to it. On the left-hand side of the arrow, those are what are referred to as our reactants. And again, those are our starting materials in a chemical reaction. On the right-hand side of the arrow are what are referred to as our products, which are the stuff that's obviously made as a result of the chemical reaction. So left-hand side reactants, right-hand side products. Now, a lot of times in chemical reactions or equations, you will be given a lot of other information other than just the reactants and the products. Very commonly, you're given the states of everything. So are things in sort of solid, liquid, gas, whatever it may be. Sometimes above the arrow, there's a lot of information, as we'll talk about here in just a second, sort of given to you sort of on the arrow as well. That helps you understand maybe what is going on. We'll get back to that, I think. So some of the other important information that we do see in equations are really the states. So next to our formulas, we oftentimes will see either G for gas, in kind of parentheses, S for solid, L for liquid. So again, we got some gases here. That should be a capital O, like carbon monoxide. So that is a CO gas there, some gases going all the way across there. We have some solids, gases, and liquids. We oftentimes think of sort of writing chemical equations for chemical changes and stuff like that, but we do also write sometimes chemical equations for physical type of changes that are occurring. And most commonly, we'd write a chemical equations for kind of changes of state. So if we look at this on the bottom, that is water on the left and water on the right. The difference is the water on the left is a liquid going to water that's a solid, that's basically forming ice. So that is the physical process, right, of freezing. And we can write an equation to illustrate that. Same thing, the second one on the bottom there, that's liquid water going to gas, or water in the gas state, which is steam. That's the process of evaporation. So although a majority of the time we do use chemical equations to represent chemical changes and chemical reactions that are occurring, we can also obviously use a chemical equation to represent some type of physical process that is occurring as well. Another common process is taking something, for example, and dissolving it in water. And sometimes you will see H2O written on top of the arrow to indicate that whatever you're taking, you're dissolving in water, and that is sodium chloride solid to sodium chloride that is aqueous. Aqueous means that it is a water environment. Sometimes, again, people have a question of, what is the difference between, say, a liquid and something that is aqueous? And there is a difference. A liquid is really a pure substance by itself. So for example, if you just had water by itself, that is considered a pure liquid. Something that is aqueous is typically what is referred to as a solution, which is a homogeneous mixture. And basically it's made usually by taking something, for example, like water, and taking something and dissolving it in it. So if you took water and took some solid sodium chloride, like we see kind of really on the bottom there, and the sodium chloride will dissolve in the water, you will get a sodium chloride solution, which will get the aqueous symbol. So aqueous usually implies that something was taken and dissolved and you made a solution out of it. Something that has just the pure kind of L version of it, or liquid, is really a kind of pure substance by itself, nothing else sort of dissolved in it. Any questions on that there? Now, a couple other things that we sometimes will see up on top of the arrow. We will sometimes see like the little delta symbol or triangle. That oftentimes means that heat is involved. We'll sometimes see things written up there like platinum, maybe like H+. These sometimes are what are referred to as a catalyst. So sometimes catalysts are very often written on top of the arrow, and catalysts are a couple important things. Catalysts are not reactants. They are not products. They actually do not get used up in a reaction. In most cases, catalysts are there simply to basically speed up the reaction. So a lot of times catalysts are added to a reaction to speed it up. So that's usually the purpose of a catalyst, to speed up a reaction. But again, it's not really consumed in the reaction. Again, it's not considered a reactant or product. Most of the way, or a lot of ways that catalysts work, is they sort of provide a sort of common place where everybody's sort of attracted to, brings everybody sort of into the central location, allowing the reaction to sort of take place a lot faster than if the catalyst was not there and they had to kind of float around and find each other, or fly around their gases and find each other. So you add a catalyst, it kind of brings everybody close to each other. That allows the reaction to take place a lot faster, and usually you will see a reaction speed up as a result of that. And that's typically why they are added. A lot of reactions are spontaneous, which means that they will occur at a specific temperature and conditions. But a lot of reactions, even though they're spontaneous, they actually occur super slow. So sometimes people think if a reaction is spontaneous, you snap your fingers and the reaction happens really, really fast. But when somebody says that a reaction is spontaneous, what they're really referring to is under those conditions, could be really fast, could be super slow, but at some point those guys will come together and the reaction will take place. So Sometimes people, again, think about spontaneity in terms of being very, very fast in terms of a reaction happening. But again, it doesn't necessarily mean that. So a lot of times catalysts are added to it. The formation of ammonia, NH3, is actually a spontaneous reaction, but it's like super slow. If you don't put a catalyst in it, you'll be there all day for it to sort of happen. Any questions on that? Yeah. Yeah, so which is outside sort of our class in a sense, but I think we talked maybe a little bit about energy already and activation energy, I think, right? Maybe. So if you remember those sort of diagrams with the hills, that's basically what a catalyst does, is by finding sort of an alternative path for that reaction to take place, it actually lowers the overall energy needed for the reactants to sort of get to the other side. And by lowering the energy, allows more reactants to actually get to the other side and the reaction take place. And thus the reaction sort of happens a lot faster than it would if it wasn't there. But essentially, and I think we looked at these here, but essentially there is that activation hill that the reactants has to climb to get to the other side. And what a catalyst does by finding that alternative pathway really lowers that hill. And again, it allows more reactants basically to get over there a lot quicker than it would without it being present. Other questions? Okay, so let's talk about balancing equation. There's several steps to balancing equation. And most people just kind of, do a little trial and error, but it's really important, especially if you are given the reaction in words, to, as I mentioned before, not really worry about the balancing part of it, but make sure you worry about, did I get all the correct sort of formulas? So a lot of times you may have the reactants given to you and you will have to maybe predict what's on the product side. And again, that's a very common place where people kind of mess up because they try to balance and write the equation at the same time. So make sure, again, get the proper formulas. Then you want to actually start balancing it. Again, the only thing that changes are the coefficients in front. Never ever, again, change the small numbers, the subscripts. Never put big numbers between letters. Some people do that weird things. So only those guys in front. When you're all said and done, really, you should end up with obviously the same number of elements on each side. So it's a good idea to take a moment and make sure that you actually did that. There are really two rules when it's all said and done. First rule is, when it's all said and done and you feel like you have a balanced equation, it needs to be all whole numbers for the coefficients. So the coefficients need to be all whole numbers always. And it does need to be the simplest set of whole numbers. So some people may see larger numbers to balance everything, but if you end up with sort of larger numbers and you're able to reduce down all those coefficients and still get whole numbers, you should do that. So for example, wherever I just went, if you had an equation where you had 4a plus 2b gives you 6c, and we'll just pretend that this is balanced. Obviously, if this was balanced, we could actually go through all these coefficients, basically divide by 2 and still get whole numbers. And you should do that. And that would get you the properly balanced equation. So sometimes that occurs a lot because, like I said, sometimes people could kind of see the larger numbers to balance it. So what you want to do is, after you make sure, obviously, you have all the coefficients that are whole numbers, just want to make sure you can't reduce down everybody by a common number and still obviously have whole numbers when it's all said and done. Any questions on that there? All right. There's another approach, in case you like this approach better, but we'll skip it. You can look at it later if you like. All right, let's just get into some here. So let's take a look at one here together. Okay, so if we were going to balance this equation, I personally think that a good approach is to make like a little table what you got going on. So we got the reactant side, product side, list all your elements, nitrogen, oxygen, hydrogen, and sort of take an accounting of what you got to start with. So looking on the left-hand side, we got 1 nitrogen. Right-hand side, we have 2 nitrogens. Left-hand side, an oxygen, we have 1 oxygen, which is obviously right here. Right-hand side, we got 1 oxygen, which is right there. Left-hand side, we have 2 hydrogens, and right-hand side, we have 2 hydrogens. So again, this helps you maybe focus in on where maybe you should start. So clearly everything is balanced except for nitrogen. So that seems like a very good place to start. So we will start by balancing the nitrogen by simply putting a 2 in front, again, the coefficient. When we do that, that now gives us 2 nitrogen. Distributing that 2 to everybody that is there, including the oxygen, will give us 2 oxygen, and we do get 2 hydrogen. Very common what happens as you go to balance equations is you fix one thing and kind of screw up something else. So now we can look at our table and we can see we fixed our nitrogen, but kind of screwed up our oxygen. So to fix our oxygen, we could simply go to the other side and also put a 2 in front of our oxygen. It's not just in front of oxygen, but it's also obviously in front of the hydrogen there. So on the right-hand side, we have 2 nitrogens. Oxygen, again, distributed to everybody that is behind it. That is 2 times 1 gives us 2. And for hydrogen, we now have 2 times 2, which gives us 4 in this case. At this point, we can now see we balance everything but the hydrogen. So back to the left-hand side there, and we're going to put a 2 in front of it. And that will give us 2 nitrogens, 2 oxygens, and 2 times 2 would be 4. And that would be our balanced equation at that point. Again, we got the same number of elements on each side. And that's sort of what most people do, put a number on one side, put a number on the other side. At some point, if you're doing it correctly, you know, everything should kind of fall into place at some point. Any questions on any of that there? Okay, so why don't you give this one a go here. All right, so take a couple minutes here, see what you come up with. Make our table. We got some carbon, we got hydrogen, we got oxygen, reactant side, product side. Left-hand side, 3 carbons, right-hand side, 1 carbon, left-hand side, 8 hydrogens, right-hand side, 2 hydrogens, left-hand side, 2 oxygens, right-hand side, we got 2 oxygens there, plus 1 more there. Does give us 3 in terms of oxygen. In this case, not much balance, so perhaps the easiest thing to balance would be to start with the carbon. We could simply balance that by putting a 3 over here on the right-hand side. We put a 3 on the right-hand side, that gives us 3 carbons. We still have 2 hydrogens. Now in terms of oxygen, 3 times 2, which is 6, plus 1 more, gives us 7 in terms of the oxygen on the right-hand side. At this point, probably the next easiest thing to balance, since hydrogen's by itself really on both sides and oxygen's in a couple places, is probably the hydrogen. And the hydrogen, we have 8 on the left, we have 2 on the right, so we can simply balance out by putting a 4 there on the right-hand side. When we do that, we still have 3 carbons. 4 times 2 is 8 hydrogens. Oxygen, we're up to 3 times 2 in the first one, which is 6, and 4 times 1 in the second one, which is 10 at that point. That means we can now simply balance it out by going to the left-hand side, and all we need to do is put a 5 there in front of the oxygen, and that should give us 3 carbons, 8 hydrogens, and 5 times 2 would be 10 oxygens. Any questions on that particular one there? Now, do you have to make the table? You don't, but it's probably helpful to do so. If not, I would probably at least check it up at the end there just to make sure. You know, I've seen a lot of people turn in things that say it's balanced and it's really not. Do you have a question? The 10 for the oxygen? Yeah. On the left-hand side is 5 times 2, which is 10. And on the right-hand side, it is 3 times 2, which is 6 there, and 4 times 1, which is 4, which if you add those together, also give you 10 on that side. Yeah. Other questions? Yeah. So this would be applicable there if you're asking something like this, like if you're given this in words, like you took some propane plus some oxygen to form carbon dioxide and water. you want to remember that when you see something like, hey, you took propane plus some oxygen or molecular oxygen, that the formula that you use would be O2, not just O. So it's a very common mistake if people have something in words and they need to turn it into formulas. You know, for those diatomic molecules, you just use like O or H for hydrogen. When they are by themselves, you want to make sure that you're starting with the correct formulas, which would be those two guys. Other questions? All right, let's try another one here. Maybe. All right, diboron trioxide reacts with water to form boric acid. So why don't you give that a go? So this would be what we were just talking about. You want to make sure, again, you get the proper formulas down first and then balance it. Look, so again, we got everything in words. So we just want to make sure, first off, forget about the balancing part, that we get the right formulas. So diboron trioxide tells us like type 3, which means that is B2O3, reacts with water, which is H2O, and forms our boric acid in this case. So at this point, we have the correct unbalanced equation here, correct formulas down. Now we can actually do the process of balancing. So we'll have our reactants and our products. In this case, we got B, O, and H. Left-hand side, obviously, we got 2 borons. Right-hand side, we have 1. Left-hand side, we have 4 oxygens. And again, that is 3 from here and 1 from there. Right-hand side, we have 3 oxygens in this case as we multiply that in. Left-hand side in hydrogen, we have 2, and right-hand side, we also would multiply the 3 in for the hydrogen as well. And that would get us 3 in this case. Any questions so far here? At this point, not much to work with other than maybe the boron there on the right. So we'll go with a 2 there. Putting the 2 in front does give us 2 borons. Now, in terms of oxygen, we do need to take the 3 in, which gives us 3, but then we also need to multiply by the number in front. So that is 3 times 2, basically, which gives us 6. Same thing for the hydrogen. We need to multiply the 3 in and then multiply by the 2 that's in front, which gives us 6 here. Any questions on that there? Clearly, at this point, we can't touch anything on the right as we already put a coefficient there. So we'll go to the left here. And really, the easiest thing probably to balance again here would be the hydrogen, as it's in only one thing on the left, as opposed to the oxygen that's in multiple spots there on the left. To fix the hydrogen, we would need a 3 in front of it. That gives us 2 borons, gives us 3 oxygens there, and also another 3 there. Which actually gets us to 6 oxygens, takes care of the oxygen as well. And 3 times 2 gives us 6 there for the hydrogen. Any questions on any of that there? Okay. All right, then let's try one more here, I think. All right, balance this guy up, see what you get. NH3O2, a little NO, and H2O there. Okay, let's take a look. So kind of doing the same thing. We got reactant, we got product, we got some nitrogen, hydrogen, and oxygen. Left-hand side, 1 nitrogen, right-hand side, 1 nitrogen. Left-hand side, 3 hydrogens, 2 hydrogens on the right. Left-hand side, 2 oxygens and 1 oxygen and 2 oxygens there. It gives us 2. So obviously everything's balanced except for the hydrogen. So probably would make sense to go on both sides in this case, but sometimes you need to do. Since we have 3 and 2, common number there would be 6. To get my hydrogen on the right to 6, I need a 3. Get my hydrogen to 6 on the left there, I do need a 2. That is going to give me 2 nitrogens. That will give me 6 hydrogens. That will give me 2 oxygens. Right-hand side, 1 nitrogen. That will give me 6 hydrogens. And oxygen 1 in the first guy, and also 3 here now in the second. Gets me 4. At this point, probably nitrogen would be the next easiest thing to fix. We could put a 4 in front of the nitrogen. And when we do that, we actually only need a 2 would be a better number there, since we need 2 on the other side. So we could put a 2 in front of the nitrogen on the right, and that will give us 2. That then will give us still 6 hydrogens. Now, in terms of oxygen, we have 2 there, and we have 3 there. which would be 5 in this case. Any questions so far? At this point, we pretty much have coefficients in front of everybody except for the oxygen, which is where we want to go next. We clearly do not want to erase our coefficients because we're kind of going backwards. So we basically need to turn a 2 into a 5. So in this particular case, we can do that, and we could do that by using actually a fraction of 5 divided by 2. And if you do that, you end up with 2 nitrogens, 6 hydrogens, and when we take 5 halves times 2, we end up with 5 in this case. Is that the balanced equation? It is balanced, but it's not a properly balanced equation because all of our coefficients are not whole numbers, right? So although we can use a fraction here to balance it, which sometimes you do need to do, you cannot leave the fraction as part of your balanced equation. So we do need to go back through actually and get rid of the denominator by multiplying everybody by 2. And that will yield me 4NH3 plus 5O2 gives me 4NO plus 6H2O. And if I didn't screw anything up here, this should still be balanced. We got 4 nitrogens on the left, 4 on the right. We got 12 hydrogens on the left, 12 on the right. We got 10 oxygens on the left, and again, 4 in the first one and 6 in the second one gives us 10 on the right. So this illustrates a very good point. When you're balancing equations, there are oftentimes situations where you might need to use a fraction. You absolutely could use a fraction to balance it, but you cannot leave the fraction. So you do have to clear it by multiplying everybody by the denominator to do so. Any questions on that? Now, sometimes people go like, how do I know what fraction to choose? It's a pretty simple formula. The fraction is pretty much the number you need on top. And the bottom number should match the subscript. So if you remember, we needed 5, and this number matches that number there, and you'll never go wrong on picking the right fraction that you need in that particular case. Any questions on balancing there? Okay, so I want to try a few more here just to make sure. All right, so why don't you do, let's do C8H18 plus O2 CO2 plus some water. Why don't you do Ca3 PO42 plus Na2SO4 Na3PO4 plus CaSO4 and let's do K3PO4 plus all right. Okay, let's take a look, see how you're doing. We'll start with the first one here, which was C8H18 plus O2, CO2 plus some water here. Okay, so kind of doing the same thing, reactant side, product side. Here we got carbon, hydrogen, oxygen. We got 8 carbons on the left and 1 on the right. We got 18 hydrogens on the left and 2 on the right. And oxygen's 2 on the left, and we got 2 in the first one and 1 in the second one there, going to give us 3. So again, here, the carbon, probably the easiest to sort of fix. We could just simply put an 8 in front of it. And when we do on the right-hand side there, we get 8 carbons, 2 hydrogens. Now in terms of oxygen, that is 8 times 2, which is 16 plus 1 more, should get us a 17 on the right-hand side. Now, again, the probably easiest thing to fix would be the hydrogen. Again, we do have oxygen in a couple of spots on the right, so probably don't want to play with those. So looking at hydrogen 18 on the left, we got 2 on the right. I believe that should be a 9 that should go there. That is going to give us 8 carbons, hydrogens. 9 times 2 is 18. Oxygens, we are now up to 16 here plus 9 here. And that is a lot. That's like 25 maybe or something like that. I think at this point, we have a similar situation as we talked about before. We don't want to really mess with any of these numbers as we kind of have them locked into place. The only place to go next would be the oxygen on the left. And again, in this case, we would probably want to use a fraction. It would be an easy way to kind of fix it. And if we were to do that, we would probably go with something, again, number on top, what we need, which is 25. Number on the bottom would match this number here, which is 2. And that would then give us 8 carbons, 18 hydrogens, and 25 oxygens. Again, it is technically balanced, but not correctly balanced as we still have the fraction. So we do need to go through here and multiply everything by the denominator. And that would get us 2 of the C8H18 plus 25 O2, 16 CO2 plus an 18 H2O. And if we did this correctly here, 2 times 8 is 16 carbons on each side. 2 times 18 is a lot there, 30 something, 6, I guess, on each side. And we also have our 50 hydrogens, 32 in the first one and 18 in the second one. So it is balanced. Any questions on that there? Okay, looking at the next one, which was our Ca3PO42 plus Na2SO4 gives us Na3PO4 plus a little CaSO4. Now, when you look at an equation like this, hopefully you notice a couple of things. First off, there's a number of polyatomic ions on each side. And for example, here's phosphate, and here's phosphate, here's sulfate, and here's sulfate. Now, if you want to, you could definitely go sort of element by element like what we've done previous. But sometimes it's much easier when you're dealing with polyatomic ions to actually keep the polyatomic ions together and balance them as whole units. And you don't have a lot of sort of multiplying in. So if we sort of take that approach, we got 2 phosphates on the left, 1 on the right. So we could simply balance the phosphates by putting a 2 in front of it. What that now does is give us 2 phosphates here on the right, 2 on the left. That immediately changes our sodium to 6, and that also tells us where we should go next. So if we go to the left to fix the sodium, we would need to put a 3. That then gives us 6 sodiums, but also changes our sulfate to 3. And we could fix that by finally going to the right and putting a 3 in front of the sulfate. Also gives us 3 calcium, which is good because that is ultimately what we need. So sometimes it's much, much easier when you have a lot of polyatomic ions in an equation and they look the same on both sides to keep them together and balance them as whole units rather than going element by element. You could definitely go element by element, but there's a little bit more room for error as you got to do a lot of multiplying in on those parentheses and all that kind of stuff. So sometimes a lot faster. And this is usually what will happen is at some point, everything again will just sort of fall into place if you kind of balance out those polyatomic ions. Any questions on that there? Yeah. Can I show you the other way? Yeah, it would be sort of the same approach. You would have to go again, every element there, which is phosphorus, this is oxygen, this is sodium, this is sulfur. So again, as you can see, it's a lot of elements to try to keep track of. And again, you just got to kind of do the same thing. So you would have obviously 3 calciums, On the left, you would have 1 calcium there on the right before we started. Phosphorus, we would have 2 on the left and 1 on the right. Oxygen, we would have 8, but then you also have to look at the 4 that you got over here. So that is 12. And you can see it's a lot more complicated to kind of go element by element here, because there's a lot more you got to keep track of, multiple spots where you have oxygen. And I would highly recommend perhaps not doing it in a case like this where you have these polyatomic ions. But again, you would have to kind of count over on this side. And again, you got 4 and 4, which would be 8. Your sodium on the left there would be 2 and 3, and then sulfur was the last thing, which 1 and 1. So again, even when you look at the table to start with, there's a lot more stuff to look at and go, where really should I start and stuff like that. Again, probably in this case, you might start with the calcium and kind of work your way through. But you eventually get there. It's just a little bit more difficult because a lot of times those polyatomic ions, especially when you have multiple ones of them, you obviously have the parentheses and you got a lot of distributing in and stuff like that. And especially if you got them on kind of both sides and everything, and you got some oxygens in multiple spots, it's just a lot to sort of keep track of. So as you can see, it's going to be probably a little bit more difficult to go through this, but you could. But it'd probably take you A, longer, and B, a little bit harder to do and stuff like that. So again, in my case here, I would probably, like I said, start with the calcium and kind of work my way through. Or again, you could have started with the sodium and went with a common number of 6. So there's multiple ways you could have approached it to get there. Same question or different question? Same, yeah, okay. Other questions? Okay. So yeah, it's a good way of doing polyatomic ions when you have an equation. And like I said, it's a lot quicker way of doing it, and usually a little less room for error in those situations. So let's take a look at the last one, which was, where's that one right here, which is K3PO4 plus, what did I end up with there? CaSO4, I think. And K2SO4 plus Ca3. So at this point, again, I would look and see we have some of those polyatomic ions once again. And in this particular case, we do have some polyatomic ions on both sides. They're actually the same number. So we have 1 sulfate on each side. So that would also point us to maybe the phosphate's a good place to sort of start with on this one. Again, we look on the right-hand side, we basically have 2 phosphate units and 1 phosphate unit. So we could easily fix that by just putting a 2 in front of the phosphate on the left. That gives us 2 phosphates. And then again, that immediately changes our potassium now to 6, which is again, also the next place you probably want to go to fix it. So we go to the right-hand side to get our potassium on the right to 6. We would need a 3. That does give us 6 potassiums, but then gives us now 3 sulfates, which tells us really where to go next. So if we go to the left-hand side, we would put a 3 in front of the sulfate. Again, that also gives us 3 calcium. And as you can see here, that is exactly what we needed. So again, at some point it falls into place, and it's a much quicker sort of approach than, again, going sort of element by element when you're dealing with sort of polyatomic ions involved. Question on that there. Now, clearly we didn't do that on the previous ones that we did because there really wasn't polyatomic ions. And obviously for this to work and to do this sort of technique, you'd obviously need the same polyatomic ion on both sides, right? To kind of make sure it works. Any questions on equations or anything? Whenever you have an equation, you should always make sure that it is balanced. So again, if you see coefficients in the equation, it's probably balanced. You should take a second to make sure. Definitely, if you're given an equation, there are no coefficients, you should definitely take a very hard look at it to make sure that it is balanced. Pretty much everything we do in chemistry needs the equation to be balanced. So you never really will do anything in chemistry where you kind of proceed for the most part with the unbalanced equation. So it always needs to be balanced. So whenever dealing with equations, that's really the first thing you should always look at and think about, is this equation balanced? And if it's not, you probably should go for it, then balance it is probably the right move. Any questions there? All right, that wraps chapter 6.